Hi, welcome to the Signal Path. What are we looking at? Well, I have another product review for you guys. This is the National Instrument VirtualBench. It is a full lab in a box, and you might have heard about it already. It's been on the market for some time, but I've gotten one here in the lab, and I'd like to show you how it looks like, what it does. We're going to do a teardown, a bunch of experiments. We're going to look at the software. It should be pretty interesting. So let's not waste any time. Let's get right into it. Alright, let's go ahead and take a look and see what's inside this unit. Now, from the weight and the dimension of this, we can easily conclude that this is going to have a switching power supply and not a linear power supply. So every voltage on this, the voltages that feed the multimeter, the function generator, oscilloscope, as well as the internal power supply for one of its main instruments is going to be all derived from that switching power supply. So they have to have done a pretty good job in making sure that that's very well isolated. Of course, I'm not surprised because NI is an expert in creating instruments in very tight spaces and a lot of analog and digital and mixed signal type of circuitry very close together, because they make some of the world's best PXI modules. So they really know what they're doing, and I expect to see that expertise laid out here in these boards that are going to be going to find in this instrument. So it's going to look very nice, I'm sure. I haven't actually seen one inside it yet, but I suspect that that's going to be the case. Now, because it has, multimeters and oscilloscopes and all that, and there's going to be sections of the board individually fairly well isolated from each other, and each of them is going to have its own functions all very close together. But I suspect that there should be one main processor that collects information and controls everything in a global fashion, because after all, these instruments are all connected and locked together, and they all talk to the same GUI at the end, which runs on the computer. So I expect that to be the case. Now, the 4 legs I've removed, and that should allow us to remove the back of the panel. The device is right now upside down, so this is the bottom, of course. That's why the stickers are all there. And this is where the fuse axis is, but once we lift this, you're going to see everything anyway. So let's go ahead and take a look. There we go. Ooh, there it is. Ah, look at that. That looks really, really nice. Let's take a look at here for a second, just to appreciate what's going on. You can see that in the cast there is a label here indicating that insulating material have to be put here and here. This likely are also RF absorbers to ensure that not just electrically isolated, but perhaps there is no EMI reflections and so on happening inside the unit. You can also see that this spongy mesh conductive material is making electrical contact to this. This is metal. And this is going to touch, where is it going? There it is. It's going to touch here, and that's going to make sure that there is a good ground connection to here. And these little pieces of tape with these jaggedy edges are going to make sure that there's a good connection to this. So they really want to put this in a Faraday cage, in a nice ground all around all the circuitry, so that the behavior is well modeled and well captured, and they can rely on it. You can see that there is even some insulating material around here, of course, and this is because once you remove that, this area of the PCB is exposed, and they want to make sure that there is nothing in here that can accidentally connect to the PCB. If you put your screwdriver or something in there, or if you're putting your finger in there, that you're completely isolated from the PCB. So a lot of attention to detail, clearly, as you would expect from an NI instrument. So let's go ahead and put this bottom plate away, since we don't need it anymore, and take a closer look at the board itself. Now, the layout is very nice. Like I said, I was expecting that. And you can see that here is where the multimeter section is. That's why these fuses are here, high quality fuses again. And you can see there's some further shielded section here. I suspect this might be the portion of the multimeter responsible for the conversion and the very sensitive analog regions, so they're even further isolated. And this section over here is going to be the power supply section. So there's a bunch of analog circuitry, current monitoring fuses, the resistor fuses, and so on, all concentrated here. This component over here is a lattice FPGA, and this is a very small FPGA, likely some glue logic or some low-level functionality. This is obviously not the main FPGA of the board. It can't possibly be. And this is the area for the digital I/O, and the logic analyzer is all at the bottom, so that must be on a different board, because there's no way this is the only board. There's got to be something else. The fan obviously over here, blowing air into the unit or out of the unit, I can't quite remember, but this is not where the main switching power supply is. The main switching power supply is kept all the way on this side. So the very sensitive analog portions, which are the multimeter, the oscilloscope, are here. The switching power supply is here. Separated from each other. I don't see the main FPGA yet, but the layout is very nice and clean. A couple of non-populated components, but other than that, a really nice layer of this board. If you pay a bit more closer attention, you can see a very large connector footprint here, and that is what is going to connect this board to another board, and I suspect that on the other board is where we're going to find our main processor unit, and that should be on the other side. Now it looks like by the legs that we see here, the top and the bottom of the unit are screwed together from the same screws, and the screws were actually quite long, you can see, so that makes sense. And if I were to lift this, there we go, that opens that. Let me just put that aside for a moment. Oh, it looks very nice on the other side too. This is the top of the unit, where the logo is, of course, and you can see another conductive spongy material here which makes contact to the other side. Really nice grounding scheme, again, just like we saw on the other side of the board. We just put that down, and ta-da, here we go. Now we can see a little better what's going on again. Here's the fan that we were just looking at. This cable here is the Wi-Fi antenna signal. Let me put that over here, and there it is. Here's our DC-DC, not our DC-DC, I apologize, our switching power supply, and you can see that it's of course also completely shielded, as to be expected. And this is the bottom of that board that we were just looking at, and if you look inside like so, we can see that that's the massive connector, but that's now the other side of it on the other board, and you can see that there's a daughter board connection which just makes contact between the top and the bottom. And again, a little close attention here, we can clearly see a very massive footprint of a BGA package. That has to be our main processor, again most likely an FPGA, and you can see a whole bunch of length match differential low voltage signaling traces there, feeding possibly the DAC that is responsible for the arbitrary waveform generator, or the ADCs that are collecting data from the oscilloscope channels. But a whole bunch of ground stitching here, very nice and clean layout. There appears to be some flash memory here, a whole bunch of perhaps diodes there. These must be the protection circuitry. Yep, these are the protection circuitry for the I/O lines on the logic analyzer. So that also makes sense. This is the cable. You can see it's going up and down through these specially cut out sections of the PCB to make sure that this cable stays nicely and neatly in place, and that's the Wi-Fi signal going into here. So it's possible that this right here is where the Wi-Fi chipset is, again separated from everything else. There's something here, I'm not sure exactly what that is at the moment, but this is an unpopulated connector board of some kind. Here's a light pipe and two LEDs here, which is the light in the front indicating Wi-Fi activity. This is the main switch that turns it on and off. Looks really nice and really clean, and you can see that the screws responsible for removing this board are labeled, and it looks like it's easier to remove this board than the board at the bottom. So let me go ahead, take these screws out. We can remove this board, and with it should come out all of the BNC connectors and the logic analyzer connectors and so on that are connected to this top board. So you can see that how the functionality is broken out. Obviously anything that's below this line here is on this board, anything above is on the other board. So very nicely put together. Yeah, very nice. Let's go ahead and take it out. Alright, I went ahead and I removed very carefully the Wi-Fi cable from the board so that this is easy to remove. And now we can look on the other side and look at it. It's very nice. Let's talk a little bit about that. Now unfortunately the main processor or FPGA is covered, so I can't tell what's in there. I can remove the heatsink and take a look, but I'd rather not disturb it and let it be the way it is. But you can just quickly take a look and see what's going on. Now, as I suspected, you can see here's our Wi-Fi module, completely separate and isolated. You can see my light there. I'm trying to get no reflection, as little reflection as possible. Here's some crystal. Here's some more input circuitry for the logic analyzer section, some more flash memory, DC-DC converters, more memory right here under the heatsink. Now there is some more circuitry in here. These are the two analog oscilloscope inputs. Obviously this is the analog front end of the oscilloscope where the different attenuator settings and amplifiers and single entity differential conversion and all those wonderful things happen. This is an analog devices ADC. This is a 500 megasample per second 8-bit 2-channel A to D converter. It has an SFDR of about 55 dB and an ENOP of 7.5 dB, so fairly reasonable to use for an oscilloscope. The trigger signal, here's our arbitrary function generator. This is most likely the DAC for the arbitrary function generator, but I cannot see what part that is, but this is a logical location for it in order to be close to, of course, the output there. Some more DC-DC conversion circuitry and so on. Now if I were to flip this on the other side, now we can take a look at a couple of these components that might be of interest here. This component right over here is just a DC-DC converter control circuit chipset for generating a whole bunch of different voltages. This here is a synthesizer coupled to this crystal right there, most likely providing the clocking, obviously, for the DAC that is sitting there, and perhaps even for the ADC. But it's pretty straightforward, otherwise very nice layout. There's no mistakes in it whatsoever. I'd imagine there's multiple iterations of this has gone through, of course. Now one thing that's interesting is this part over here, because it's not populated, but you can see all the pins are going differentially to these, and this has a connector there, so it obviously must have had some function. I wonder what they were doing with this. I can't quite recognize what's going on because there's nothing populated, so I have no way of knowing what that is, but perhaps this looks familiar with somebody, and you can leave it in the comment if you think you know what that is. But as you can see, the design is very nice of this board as well, and we can also turn our attention back to the other side. This board, this is our Wi-Fi signal. Let's put that aside. You can see the multimeter inputs. They look fairly nice, reasonable. I think they have good structural integrity, soldered quite nicely in there. And there's also, because the holes in the front panel are quite small, that also provides some further structural integrity over there. There's some another lattice part over there, some isolators and so on, and there's some power transistors perhaps which control the output of the main power supply unit. More analog DC-DC converter circuitry there. This is obviously the interconnect between the two boards. The whole switching power supply over here, fairly nicely shielded and separated. It looks really nice. There's more light pipes over there for the individual and the indicators of the built-in power supply. More isolation again. It makes sense that we have isolation on this side and equivalently on the other side, because that's probably where the analog to digital conversion for the 5.5 digit multimeter takes place. Here's our shunt resistor over there for the current measurement. Other than that, very nice, very clean, compact. There isn't much of a waste of space in there. Obviously they could have put some more things in here if they wanted to, because there's obviously some more empty space, and who knows, maybe they have some plans for VirtualBench too, and I have some ideas that might be helpful as we go along. I'll talk about them, but let's put this back together, turn it on, take a look at the software and start using it. I'm pretty excited to do some experiments with it. And here's the VirtualBench sitting in the lab. I put it on top of my Rigo synthesizer just to give you an idea of the relative size. It is a pretty light and compact unit. It's 10 inches in this direction, 7.9 inches deep, and 2.9 inches tall, and it weighs just over 4 pounds, about 2 kilograms. Now I'm going to go through the specifications, of course, in detail, but let's take a look at the front panel and see what it looks like. It has a very traditional setup, so it's very easy to use and easy to recognize. At the bottom right, you have the digital multimeter ports. It has that typical high and low measuring voltage, resistance, and diode, as well as a milliamp and amp range inputs for measuring current. It's Cat2 rated, as you can see written in the front, 300 volts, and we'll take a look at that in more detail. At the top of that, we have channel 1 and channel 2 of the oscilloscope inputs, 100 megahertz, 1 gigasample per second. If each of the channels are individually used, or 500 megasample per second for both channels. The probe compensation outputs are right next to it. We also have the function generator output, which is actually a 20 megahertz, 125 megasample per second function generator. It's an arbitrary function generator, but from the software that's provided right now, you can only set it to have a specific functions outputs. And then we have the trigger port here, which is both an input and output, configurable in software, and it has several functions, and we will see that too. In the middle, we have the DC power supply. Now, the DC power supply doesn't use a traditional kind of banana plug type of ports. It uses this proprietary connector here, which NI supports, and we will take a look at the list of the accessories, and that plugs into here and screws in, and then it has little terminals where you can put a wire in and screw the wire down. It has those screw terminals.
Now they've done that obviously to save space, because if they were to put in, you know, plus and minus 25 and plus 6 volts and the two different grounds, you're going to need quite a bit of extra connectors, and they didn't want to do that in order to keep the front plates and the whole thing quite small. So they've gone that route. It's a little inconvenient if you want to just quickly measure something, because you're going to have the cable ready and have it be able to be screwed in, but it's a compromise basically in terms of having a very flat finish as well as a small unit, you know, versus some convenience. And yeah, we'll see how that works out. On the left, we have the digital I/O ports. It has the same connector, just more terminals, but it doesn't have the screw in on each side. I guess they assume that because this is so much bigger, it has better structural integrity anywhere, so anyway, it's not going to be pulled out. I would have liked to see that also be able to be screwed in just like the other one. At the top center, we have the 32-channel logic analyzer plus clock 0 and clock 1, which we will see in software again. It has again a very typical type of connector, and it comes with a cable, and we will see that. Power plug right here, and the activity of the Wi-Fi port right there as well, that we saw the light pipe from inside of the unit when I was doing a teardown. So very nice in the front, very clean and easy to use. So let's move on. And here's a view of the back of the unit. It supports AC voltages all the way up to 240 volts, which is great. Here's the main ground connection that you can have to earth ground. Of course, you can lock the instrument, which is very useful, especially if this is deployed in an education lab where a lot of people come in and out, and you want to make sure that people don't move these things around. And here's the USB connector, and the USB connector has a little screw terminal here with a special USB cable, which is provided by NI, and that allows you to tie the USB cable much harder into the unit so it doesn't get accidentally pulled out, which is a nice touch, nice addition. It's very helpful again in an environment where people may move things around. And the fan, of course, the Wi-Fi antenna. So very straightforward at the back, very simple design, just like it was in the front. And well, let's take a look at some of the accessories that comes with it, and then we'll jump into doing some experiments with it and familiarizing ourselves with the software. So let's take a brief look at the accessories that come with the VirtualBench. It comes with two probes, of course, for the two channels, and these are model P6150, which are 150 megahertz probes, which exceeds the input specification of the analog scope inputs, which is great. And you can see that they have 2.3 nanoseconds of rise time, and in a times 10 settings, they have 13 to 17 picofarad of capacitance. So very typical, traditional type of probes. I'm pretty happy with them. They seem like they're good quality, and I think they might be the same ones that Tektronix uses. I'm not 100% sure, but it also comes with, you know, all the little typical things you would expect from a probe: the compensation adjustment tool, the grounding spring, as well as the markings, the probe marker colors, and so on. So very nice. Nothing to complain here. They should work fairly well, and we will see them in action. And here are the multimeter plugs, and I have to say I'm not as happy about the multimeter plugs as I was about the oscilloscope probes. They don't seem to be of particularly good quality. My biggest complaint is that this part is really small, and they don't really feel nice in the hand. The tips are quite sharp, that part of it is no problem, and of course they come with protective caps on both sides. But given that multimeter probes are so inexpensive, they could have easily upgraded this to a nicer feel with the bigger probes and perhaps some more attachments and additions to it. I mean, it will do the job, but you know, for a couple of dollars more, you can get a much better one. And as far as connectivity is concerned, you have two options, of course, either Wi-Fi, and they give you a 2.4 gigahertz Wi-Fi antenna, which is pretty nice, and you know, bends like this. So I'm not no complaints over there. And here's the USB 2.0 cable that I was talking about, that has the little screw terminal, which you can connect at the back to strengthen again, just to make sure it doesn't get pulled out. This is a very nice nice cable, and you can see it's NI branded actually. So pretty happy that they supply this to you, and I like the idea of doing that. It really helps, especially in an environment where people might move these things around. So here we can see the cable that's provided for the 1 gigasample per second 32-channel logic analyzer. Now this is great because everything is labeled. You can see it's very nice to use. It's got the proper connectors at the other end, so it's very convenient for prototyping and so on. But this is all that is provided, which means that this is all the length that you have available to you. Now, if they had provided a ribbon cable as an extension, which you could attach to the unit to give you a little bit more room and more freedom to use this further away from the unit, that would would have been great. And I think that's such a simple addition. I highly recommend that they do that, because in my case, when the instrument is sitting up on the bench, if I plug this in there, everything's just gonna hang in the air like that. I cannot reach anything with it. So this only works if the unit is right in front of you and you just plug it in right there. Then yeah, it's kind of okay. You can plug into things. But just the ribbon cable, of course, it has to meet the 1 gigasample per second timing requirements. You have to make sure it's high quality, but that's pretty common. People do that all the time. So I encourage them to add something like that. It would hugely simplify the usage of this component right here. And this is the digital I/O connector I was talking about. You can see what I was mentioning. It comes with this little screwdriver tool, so you can this is perfect size for this, and you put a wire in there and then you screw it, and this kind of plugs directly into the unit. So there you can of course have any length of cable that you want. That's not a problem. And you can see here I've prepared the power supply connector there. I've already soldered cables to it, and the cables all end into the alligator clips right there, and I've labeled the plus and minus 25 volts, the 5 in the ground, and so on. And looks pretty nice. It's fairly convenient. Once you make this yourself, then yeah, it's kind of acceptable that you can plug this, and once you plug it in there, this has the screws on each side which you can plug into the unit. So that should make it pretty easy to use. And that's everything that's provided. A little bit of extra documentation, but that's about it. So it's everything you need to get started. Nothing is really omitted, which I'm pretty happy about. And I hope that they take those little suggestions I made to heart and maybe make some modifications. But let's take a look at the software, because that's everything that is important about this, because the software has to be really, really good. And I have a couple of interesting experiments that I want to do with this. And in the process of that also, it will help us familiarize ourselves with the instrument. And here we have the VirtualBench control software. One of the nice ways this software is distributed is that it's built into the instrument itself. Once you plug it into the computer via USB, the instrument will be registered as an external hard drive, and the software is directly inside it, and it will come up with an auto run function, and once you run it, it will run the software and you're up and ready to use it. You don't have to install anything, and if you're connected onto the internet, you can actually directly update the firmware, and it will download it back into the unit, so it's always ready to go and to the latest version. If you connect it to a different computer, you'll be up and running in no time. That's really a nice touch, and I think every manufacturer should do this in order to save the hassle for the user to have to go into the website, often very convoluted, try and find something that is required for their instrument. So my thumbs up for that. It's a great idea. Right now you can see the software is in a default state. It's obviously broken up into different sections corresponding to different functionalities. Most of the screen is occupied by the oscilloscope, where you would have complex analog waveforms being displayed. That makes sense. And right now I've put it completely into default state. All the different functionalities have a little button here at the top right which have additional settings. Now here is where you can change the oscilloscope's acquisition mode. Now interestingly enough, it puts the acquisition mode in peak detect by default as opposed to sample, which is a little bit unusual. So we're going to change it here to sample mode. Now as I go through the software, I'll try to keep it brief, but I will also tell you some of the specifications of the different components as we go along, in case I haven't mentioned it in advance. You can see here that the different type of triggering modes, as you would expect from any oscilloscope. The horizontal scale is right over here, which you can change by either pushing the buttons or by using the mouse wheel. You can see that I'm changing it right now. And if I change the vertical scale, the horizontal scale into smaller, you can see that the sampling rate will jump to 500 million samples per second when both channels are enabled. And if I disable one of the channels, it will jump to 1 gigasample per second, as to be expected. Now, both channels enabled, it will you can go as high as 5 volts per division, like so, or you can go all the way down to 10 millivolts per division, like so. Now under 10 millivolts per division, let me bring that right over here in the middle, you can see that I have a little bit of offset on the model that I have. Unfortunately, I don't think there is any way to calibrate that out, as far as I know, directly from the software itself. I don't think it's supported yet. But I have spoken to the NI representatives, and they've told me that this is a continuously growing software, and that they will add features and add other functionalities as time goes along, and it's all going to be free, and it's going to be added to the software, which is a great thing, which means that this instrument is going to grow hopefully with more functionality as time passes. That's fantastic. Now, if I go on to each of the channel settings here, you can see that you can have some more options over here. You can change the channel name. The coupling, there is no 50 ohm coupling, unfortunately, but you can only have high impedance, and the high impedance is 1 mega ohm in power with 20 picofarad. Here's the probe attenuation setting, which is just a multiplication, obviously, depending on how you have your probe set up, and you can limit the bandwidth. And of course, the vertical offset can be adjusted either here or by just simply dragging the waveforms up and down. Now any number that you see, if you hover the mouse over it and use your mouse wheel, you can actually change that number directly with the mouse wheel. Very convenient. They've put a lot of thought into how these numbers are entered. You can also, of course, select it and enter it via the keypad or just push the arrows and so on. Very straightforward, as you would expect for something like this. And then right next to it is the math functions, which you can enable by simply pressing the button, and you can configure the math functions here. It supports some basic math functions like additions and multiplications and so on. Of course, it also supports FFT, which we will see, and some other little settings for the math function, as well as the volts per division, the vertical offset, and so on. Really straightforward. And you can also have all the menus pop out so that you can put them permanently on top if it is something that you tend to change continuously. Like I said, they've put a lot of thought in the software. I really like the software. It's fast, it's quick, it's very intuitive, which you would want for a type of instrument that's targeted especially for beginners who don't have a lot of equipment already. And here's the digital menu. Digital menu, oh, let's go back here. You can see that all the different digital lines are selectable over here, which you can individually select them. And once you select them, they obviously appear if the digital channels are enabled. You have 32 channels, so it's a really wide digital bus. There's also the digital IOs over here, which I will talk about later. The clocks as well as the miscellaneous functions for the trigger BNC. We will talk about that separately. You can also define buses as I2C parallel and SPI, so that you will have automatic decoding, and we'll look at that too. And I'm sure there will be more of them added into the future as the software continues to grow. Now under requisition, you can change the digital threshold of your logic analyzer. Here is set to 1.6 volt, which means that it's targeting 3.3 volt logic. The sampling rate of the logic analyzer is 1 gigasample per second, and you can see the maximum buffer size is 1 million transitions. For the oscilloscope itself, you have 1 million samples per channel. It's not a very deep memory. It might be suitable for beginners and so on who don't have a need for a very deep memory acquisition, but this is something that I don't think can be adjusted anymore. Must be limited by how much hardware memory is already allocated on the instrument itself. You can also have some triggering function, very basic triggering, edge and pattern, nothing more complicated than that. And you can also have noise reject, as well as change the delay and the level of the trigger either over here or by just simply dragging this line up and down. So really straightforward functionality from the oscilloscope. You can also have, aside from the acquisition, averaging. Of course, you can have persistent, where you can change the persistence to 10 seconds infinite and so on, and clear the display and so on and so forth. So really straightforward. One of the other things they've added that wasn't there before was this search function. Before, when you used to drag this around, it didn't used to update the waveform that as you go along, you'd have to let go of the mouse before the update began. Now they've changed that, and it will continuously update in the background. A very simple change, but it has a huge impact on how you search for waveform variations as you're looking through the captured window. So that was a great thing that they've done. You can obviously add cursors, and we can try the cursors later. Really straightforward again. Now you can also add measurements directly to what you're interested in looking at. The cool thing about the measurement menu is that all the measurements are live, so you can see them before you actually apply them. So just by opening this, you get a quick snapshot of all the measurements that are available. This is a nice touch. I wish more people manufacturers did it like this. And also you can obviously change it to all the different things that are being currently displayed. And that's about it for the oscilloscope. So let's move on to the next function. Now on the very right, we have the function generators menu. Now the function generator has a 125 megasamples per second sample rate, and its bandwidth is limited to about 20 megahertz on a sine wave. Now you can turn it on and off by just pushing this little button, and then it will enable or disable the output. Now you can see this kind of this vertical scale, which is your amplitude. So you can either move it like this, which is very convenient. So if you want to move the DC offset of your signal, you can directly do it like this, or you can adjust the amplitude like that. Obviously, as you do this, you'll see the numbers change here at the bottom. So if I want, for example, a 1 volt peak to peak amplitude sinusoid, I can just dial this down to 1. And if I want a 1 volt offset, I can just simply drag it all the way up to here until I see 1 volt. So really easy, really straightforward. The frequency is set over here. You can see that you can change the multiplying factor. And one of the other things that is common between all the different instruments is that if you go over here, in this case the output impedance, it gives you a little diagram of what the output impedance of the function generator looks like. It's a 50 ohm driver, and then depending on whatever the user load is, there's going to be a voltage divider. So this is a good warning for you to know that it is either expecting a 50 ohm signal on the other side, or that you should know that there will be a voltage division. Now there is also the pinout of all the other functionality listed here. So on the oscilloscope you can see channel 1 and channel 2 reported here, the probe compensation, all the digital IOs for the logic analyzer are listed here. You can see they're all labeled, which is great. So again, all the documentation is basically on your fingertip as well. It's built into the software. Here's the digital IO section. You can see that it has a 3.3 volt output, as well as all the other ones. We'll go over that separately, the DC power supply pinouts and the digital multimeter. So it's all built into here, which is great. Right now the software supports a sine wave, square wave, triangular wave, and adjusted DC offset. It doesn't support directly from the software an arbitrary waveform, but it is possible to download an arbitrary waveform into the memory and have it come out from that. And that would be through the automation. I'll again talk about that completely separately. At the bottom here is where we're going to have the digital multimeter. It supports all the different functionalities you would expect, as well as DC voltage, AC voltage, current, resistance, diode, and continuity test. Now the different scales of the different functions are as follows. You can go on the voltage from 100 millivolt to 300 volt range. For the current, you can go from 10 milliamp to 10 amp. And on the resistance, you can go from 100 ohm all the way to 100 mega ohm. Under 100 millivolt range, you're looking at a 0.015 percent type of accuracy, which is not bad. You know, it's reasonable. It's a 5.5 digit multimeter, and you can do 5 samples per second. So it's reasonable for what you're getting in a box like this. The diode voltage is limited to 2 volts, and the continuity test is for under 100 ohms. Basic digital multimeter functions, and we will try it out. Now on the left, you have the DC power supply. The DC power supply is triple output. It has a 0 to 6 volt, which is ground connected to everything else. So this does not have a floating ground, but the plus and minus 25 volt have a common floating ground. So they're isolated completely from everything else. So you could put them in series and so on. But you have to be careful that the 6 volt does not have an isolated ground. It's connected to the ground of all the logic lines and so on. You can see that also you can set up all the different voltages and limit the currents as you would expect in a very basic power supply. And if you click this to turn it on, you can see that it will measure and report back to you the recorded voltage as well as the recorded current, and you can see it side by side to the set voltage and the set current, which is very, very handy. And you can see this is on CV mode, obviously continuous voltage mode, because there is nothing connected right now to the output. And if you go over here, you can enable tracking so that your plus and minus power supply will track each other, useful for doing analog work where you have a dual supply configured like that. The current limit on the 6 volt supply is all the way up to 1 amp, and you have half an amp on the plus and minus 25 volt supply. The readback accuracy is actually less than half a millivolt, but you cannot set anything from the software below 1 millivolt of accuracy. But that's, again, good enough for most applications that you would want to use, again, something like this. This is a switching power supply. It is not a linear power supply as we saw during the teardown, so you have to take that into account as well. And lastly, here on the left, we have the digital I/O section. The digital I/O section is an 8-channel bus, which you can set the inputs to the channels to either be inputs or outputs. And if they're set to outputs, they can deliver up to 4 milliamp to drive something externally. You can, for example, individually set them to something. Here also, you can change the behavior of the external BNC to either behave as an input or be the MSO trigger or the function generator start, and we'll take a look at that separately as well. And as I mentioned, you can see the pinout over here. There is a built-in 3.3 volt supply that's permanently available. It can only supply 20 milliamp, but you know, a lot of times that's enough for a sensor or something that you might be trying to test out. It's mostly just used as a reference, basically, so you can maybe have a pull-up resistor or something that might come in handy. So it's nice that they have included that, and everything is separated by ground. So very straightforward software. I just went through it really quickly because I wanted to make sure that I mention the things that are important to complete the review. And now we can go and do some really basic experiments. So I have a little module that I want to characterize. Let's say I'm handed this little module and I have told that here, use the VirtualBench and find out how well it works and debug it and so on. So we're going to do exactly that. Should be pretty interesting. So here's our first setup. For the first experiment, I want to measure the performance of a voltage regulator on a module that I have for a specific IC. And I want to make sure that that IC is going to work for the range of the input voltages I'm interested in. And in order to do that, I have connected two probe wires here to the digital multimeter's voltage input, and I'm taking the cables that I made for the DC power supply out like that. Now the plus and minus 25 volt and the floating ground I don't need, so I'm not using that, but I'm connecting everything else here to this module. So let's take a close look at this and see what is going on. This is an SI 5351 dual PLL clock generator IC. It's capable of synthesizing 3 different clock frequencies which are coherently locked to the same crystal, but they can be independently set. And the PLLs are capable of integer division as well as fractional and division and so on. And we'll talk a little bit about that perhaps later on. But this IC can run from all the way down to 3 volts. But of course the power supply might vary. So there is a linear regulator on this little module that will regulate the input voltage starting from 5 volts down to the 3.3 volt, which is a nominal supply of the IC. And I want to make sure that that regulator has sufficient dropout voltage for me to be able to bring down the supply all the way down to 3.3 volts and still be able to run it while it's going through the linear regulator. And that can be easily done. I have my supply here connected to the input voltage, and here off this capacitor I'm tapping out the DC voltage of the regulator, so we can directly take a look and see what it is. And so because both of these are going to happen at the same time in the software, it should be very straightforward for me to look at the VirtualBench software and while I adjust the power supply, simultaneously look at the voltage coming out from the multimeter. So let's take a look and see what happens. So everything is connected up, and you can see that I have set my power supply here to 5 volts, and I'm right now reading nothing, about 8 millivolts. It's just some residual voltage left over on the multimeter. So let's go ahead and turn it on, and there you go. You can see that 5 volt has been enabled. It's in continuous voltage, and I'm consuming 16 milliamps. And check it out, on this side we have 3.3 volt regulated output voltage of the regulator, which is exactly what we would expect to see. Perfect. Now I can go ahead and dial down the voltage and see at what point I can no longer maintain a minimum 3 volt supply required for the synthesizer IC. We can go over here and we can do our clicks a little bit at a time. You can see that there's a tiny drop, but nothing significant so far. There we go. Now at 3.6 we are starting to drop a little bit. 3.5. There you go. At 3.4 volts, I'm already down 100 millivolts. So it looks like there's a 0.2 volt dropout voltage. Okay, let's see. At 3.3 volt supply, I'm still at 3.124, which is fine, which means that I should be able to run this module down to 3.3 volt and still be within the required minimum voltage of the IC itself. Now the minimum voltage of the IC is about 3 volts. Now if I go ahead and go down until about I hit 3, now it's 3.33, I can now go 1 digit less, and there it is. So I can be at about 3.17 volt, and I would still be able to maintain the minimum 3 volt supply. So you can see I love having multiple measurements under my fingertip in the same place. This correlated measurement style is one of my favorite things, and I did an extensive review of that when I did the Tektronix MDO 4000B, and that was a much more powerful instrument, of course, but this is the same idea. Having really coherent measurements tied together under the same view is very helpful. So now that we are satisfied about the fact that the power supply requirements are met, let's go ahead and actually establish an SPI interface and look at the outputs, and then be able to use the logic analyzer as well as the oscilloscope. And here's the setup for the next experiment. You can see that I'm using a lot more of the functionalities of the VirtualBench in this case. I'm using both analog oscilloscope inputs. I'm using some of the digital logic analyzers, the power supply, the multimeter, and the trigger input. So all of these are going to the same board that I was doing my first experiment in. Now I'm going to monitor everything at the same time to be able to take a look at the behavior of this board under some other conditions. So let me explain what everything is connected to. I have an Arduino here. The Arduino is going to program using I2C the synthesizer IC and configure its outputs to provide 2 different frequencies on channel 0 and channel 1 of the output. I'm monitoring channel 0 and channel 1 directly using the 2 channels of the oscilloscope of the VirtualBench. That's how I'm looking at the clock output of the synthesizer IC. At the same time, I have my trigger input connected directly to the power supply. This would allow me to trigger the entire system on a power supply event, and now I can see how the configuration takes place and how the output is enabled and how long it takes between those events. Basically, from startup all the way to configuration, I can monitor by a power supply event in that case, which can be quite handy. At the same time, the I2C outputs that are coming from the Arduino are also sampled and monitored at the same time with the logic analyzer inputs of the VirtualBench. The power supply of the VirtualBench again is connected here, which powers both the Arduino as well as the synthesizer IC. And I'm also again monitoring the power supply, the 3.3 volt voltage regulator, using the multimeter. So everything is used except for the function generator and the digital IOs in this experiment, and all of these are going to work together, so we should be able to make some comprehensive measurements and understand the behavior of this board quite well and look at the I2C events and all that. So let's go back to the VirtualBench software, turn it on, and do a couple of measurements and understand what's going on. Alright, so here we are. Let's take it one step at a time. Let's go ahead and power on the IC. And here we go, and you can see that again we have 5 volt applied. Now we are consuming 60 milliamp because we are also powering on the Arduino, which has some LEDs and so on it as well. And we can see our regulated voltage again at 3.3 volts. And look, we have outputs from the synthesizer. Now these two outputs being monitored on channel 1 and channel 2 are about half the frequency of one another, but not quite exactly. They're slightly off from half rate. So if I were to go ahead and trigger on channel 1, which is what I'm doing, you can see a stable waveform. As soon as I enable channel 2, you can see that channel 2 is rolling with respect to channel 1 here and there. That's because the frequencies aren't exactly the same. And the other thing to notice is that if I were to do a single trigger, you can still see that indeed the frequency is twice the frequency of the other one. But we can do a measurement to confirm that. So let's go ahead and turn channel 2 off here so we can just look at channel 1 and do some measurements. If I go over here, you can see every measurement live simultaneously being displayed. The frequency is 3.4 megahertz, and you can see that we have quite a bit of overshoot and quite a bit of undershoot here. And this is because some inductive behavior on the breadboard as well as the drivers that are expecting to see a different impedance than what they're seeing currently. I have the probes times 10 probes right now, and therefore it's producing quite a bit of overshoot and undershoot as they have very high rise time. Very short rise time. So you can see the overshoot and the undershoot being displayed at 1.5 volts or so, which is quite a lot. Now the other thing I forgot to mention is that if you hover your mouse over any of the measurements, it will give you the definition of how that measurement is being performed. And that's very important because you want to make sure that you understand the number that is being reported. Now if I select channel 2, you don't see anything because channel 2 is not enabled. So I can go ahead, for example, and pop this window out and enable channel 2, and now I see all the channel 2 measurements at the same time. We have a duty cycle of 50%, and you can see the frequency of channel 2 is 6.7 megahertz, and the frequency of channel 1 is about 3.4, so they're almost at the rate half of one and the other. So it looks all very nice, perfect. I mean, I can obviously just click something and then it will add that measurement for me down here, and this goes for anything of course, and it continues to add them, and then I can clear them if I don't want to look at it. So it's all very nice and handy. Now we are seeing this. What if I want to look at the spectral content of one of these signals and see if the spectral content matches what we would expect from a square wave at the frequency of interest? Let's see if there are other unwanted harmonics or if we have a good symmetric square wave coming out. We can easily do that by looking at the FFT of one of the channels. And enabling the FFT is very straightforward. I've already configured the FFT function over here at a center of 10 megahertz and a spacing of 2 megahertz per division. So let's go ahead and enable it. Now it is doing an FFT on channel 1. Now everything is here overlapping, but no worries. We can turn channel 1 and channel 2 off completely, and we're going to see only the FFT even though the channels are not enabled. So unlike the measurement function, the FFT will run even if you don't enable the channel. Now having said that, you look at this and say, what the heck am I looking at? Well, the reason it looks like this is because we don't have enough spectral resolution, because we are not capturing sufficient duration of time of the signal for us to produce a meaningful spectrum that doesn't have so much spectral leakage on each side. So in order to fix that, we have to capture more data. Well, we can do that by zooming out essentially. You can see, as I zoom out, I'm capturing more and more periods of the signal, allowing me to produce more spectral resolution like this, and you can see clearly that the tones there. Now I can go back, now that I'm sufficiently satisfied with it. Actually, let me go ahead and zoom all the way until we can maintain 500 megasamples per second, and that's perfect. let's turn the channel off and check it out. We can see a very nice clean view of the FFT of the signal. Now, is this what we expect? Well, this is a square wave, so we expect to see only odd mode harmonics, and the even mode harmonics should be ideally non-existent, but of course they're always going to be there in a non-ideal situation. And check it out, here's the fundamental. Second harmonic is small, third harmonic is big, fourth harmonic is small, fifth harmonic is big, and we can put markers on these and measure them. Here we go, let's choose our marker to be tracking the signal, and it's already set to math, so channel 1 is on math and channel 2 is also on math, and I can go over here and track this here until I hit the peak. If I can get it with my mouse, come on, there it is. And we are seeing 3.4 megahertz, which is exactly the measurement we saw when we were doing the measurement in time domain. And if I go ahead and bring the cursor over here, you can see the second harmonic is very small at 6.7 megahertz, and I can then drag it all the way over here, and we can see clearly what our third harmonic is, which is approximately at about 10.2 megahertz, and it gives you all the information you would want to see. You can see the difference between the two tones is 9 dB volts, and exactly what you would expect to see from a square wave. Once again, I can go here to see another even mode harmonic, or go all the way over here and see the fifth harmonic, again being quite a bit larger. And of course the amplitude is going to continue to drop because of bandwidth limitations that exist in the whole system. So you can see very easily making FFT measurements, and works quite nicely. Of course you need to know how to configure the FFT, because if you don't, you're going to see some results and it's going to be quite confusing. So that is up to you to make sure you configure the instrument properly to begin with. Now, if I were to go ahead and turn the channel off and turn it back on, you can see briefly some activities on the digital channels at the top. That's because these digital channels are connected to the I2C interface. And I have defined a digital bus over here by going into this menu, and I have defined that I2C bus to use D0 and D1 as the clock and the data lines, and to show data decoded in hexadecimal. But this is too fast, and by the time you power it on, by the time triggering starts and so on, the data is long gone. So that's why I was going to do a power supply event trigger, so we can figure out exactly how the device powers on and see the entire I2C packet being transmitted and then decoded. So let's go ahead and turn our cursors off. You're not going to need them right now. Let's go ahead and turn our FFT off. Let's enable channel 1 again, and let's start to zoom further and further out and see what happens. Did you see that? I don't know if you noticed it or not, but check it out. This looks like it's a square wave, but this cannot be right, because the scaling doesn't match anymore. As a result, this is actually an aliasing being displayed. So it means that the software doesn't handle aliasing very well, which is unfortunate, because if you're a beginner looking at this, there you go, this is a good example of that. We are doing 4.167 megasamples per second. Our signal that we are actually interested in is at 3.4 megahertz or so. So it's already over the Nyquist rate, and we're seeing a perfectly good square wave, which of course is the alias version of the signal. So it's completely wrong. And this is something they really have to address, because aliasing can be very confusing for people who have never seen it before. And this would be a problem. Now if I go under measurement, it's telling me that the frequency is 155 hertz, but we know that that's wrong. And that is definitely something that needs to be addressed. This would be a problem, especially in an educational situation. And this is something that can be fixed properly in hardware with software to accompanying the hardware that's already there. So something that should be done about that. But anyhow, so now that we are at this point, I'm going to go ahead and change our trigger from edge. I'm going to change our trigger source from channel 1. You can see you can trigger on all these channels, and I'm going to ask to trigger on the BNC and on the rising edge of the BNC. So that's great. Let's go ahead and choose a single. So now it's waiting for a trigger event. I'm going to turn the power supply off. Now when I turn the power supply on, check it out, I will get a trigger, because the power supply comes on, the circuit powers on, it waits a little bit until the Arduino boots and has some delays in there at the beginning, identifies the IC and so on, and then it begins SPI, I2C communication. And once it does that, then the output will begin. And check it out. Here's I can now zoom in. There it is. You can see some initial activity, which is meaningless at this point because I2C hasn't actually properly started. And you can also see the subsampling that I'm seeing here. It's not properly sampling it, but if I zoom out again until I see, and I can drag this and go all the way over here and then zoom in again and check it out. Here's all my I2C interaction. So it starts all the way here and I can go through all of it. You can see quite a lot of registers. There's about 150 or 180 different registers that need to be written. You can see all the activity, all the different here's the clock and here's the data and here's the decoded data, and I can go all the way. You can see there's no output, and I can continue on. Oh boy, there's a lot of it. Let's go. And once the last event is finished, you can see this is the last interaction, and here it's telling the IC enable the output, and that's when the clock starts. So I have complete timing information now. If I zoom out all the way, you can see the aliasing happening in software. That's why I'm saying it's easy to fix it. You can see from the first initial event all the way up to here, I can put a timing marker there. I can measure exactly how long that event will take place. So from, let's say, over here all the way to over here, I can measure how long that time is, and I can find out if that meets my specification, about 86 milliseconds from power on. I can see how long the entire I2C events have taken. It's taken 17.387 millisecond. So all this information is readily at your fingertip, and this is why I really like correlated coherent measurements like this, because it allows you to find problems, allows you to characterize a system which would normally be very difficult to characterize if it was span across multiple instruments. This is one of the biggest advantages of having everything connected together in one box like this. So this was just a very general example. I'm not going to go into too much more detail. I just wanted to give you a flavor of what you can do. But there's one other experiment that I want to do, and that is using the function generator. So let's leave this behind and try another experiment. And here's the setup for our last experiment. It's a really simple experiment actually. What we're doing is that I'm taking the output of the function generator, I'm feeding it directly back to channel 1. At the same time, I'm splitting it into this component right here, which is a bandpass filter. Now the output of the function generator drives the input of the bandpass filter, and the output of the bandpass filter directly goes onto channel 2. Now this is a little bit of a tricky situation because the impedance of this bandpass filter is changing as a function of frequency, and everything in there is not exactly 50 ohms. So we have the output of this is 50 ohm, the input here is 1 mega ohm and 20 picofarad, and we have 50 ohm in and out of this. So it's going to be producing some really interesting results, and I'm going to leave it as a puzzle to you guys to figure out why it is happening. I specifically done this so that we can have some discussion about people who are interested in figuring it out, and I'll talk about it when we're looking at the measurements. So I'm interested to characterize the bandpass filter characteristic of this filter, because I can look at the input signal and I can look at it after it's gone through the filter. Therefore, I should be able to judge how good this bandpass filter is. So I can go ahead and enable the function generator from the software and take a loopback measurement. So let's go back to the software and see what that looks like. Alright, here we are back at the software. You can see that what I've done is I've enabled the function generator at 10 volt peak to peak, just as a number, sufficiently large amplitude, and it is set to produce a sinusoid at 10 megahertz. Channel 1 is the direct feedback channel, and channel 2 is the signal going through the filter. They're set to the same vertical scaling, and you can see that I'm going to actually center this right here, and we're triggering on channel 1. So you can obviously see a waveform of 15 megahertz, and if I go over here and if I select channel 1, you can see that what I meant to say was 10 megahertz. Sorry, and here's a 10 megahertz frequency clearly visible. So nothing, no surprises there. It makes perfect sense. Now let's go ahead and increase the frequency here by 1 megahertz at a time and see if anything happens at 15 megahertz. Here we go, 11, 12. Now you notice that we have the amplitude of the input signal changing, and I'm going to leave that to you to figure out why. I gave a hint just a moment ago. Let's go to 13, 14, and 15, and voila, right at 15 megahertz, which is a bandpass frequency of the filter, we now see both signals at the same time. Now again, we have the red is the input to the filter, the yellow is the output of the filter. They are on the same vertical scaling. So it looks like this filter has gain, but it's purely passive. How is that possible? That's the second piece of the puzzle here. So I'm going to ask you to figure that out, but this measurement is correct. So you have the input and the output. You can see if I go to 16, the signal at the output of the filter disappears again. So this is a very, very sharp filter. At 15 we have something, at 14 we don't have anything. So if I go ahead and change the signal more slowly, let's say I change it by 10 kilohertz at a time, it still disappears even 10 kilohertz away from 15 megahertz. That's how sharp this filter is. So let's go 1 kilohertz at a time. You can see that the signal shrinks as I go up at 15.005, and if I go back down, here we go, 14.995, and it disappears again. So it has a really, really small bandwidth, just about a kilohertz or so, which is very, very narrow. And this is designed to be a multiple pole bandpass filter. It looks all great. You can see by doing this, you should be able to measure frequency response of various filters. And in fact, now that we understand that this is such a sharp filter, we can do something fairly interesting. Let's go ahead and bring the frequency down to 5 megahertz. Now obviously at 5 megahertz you're not going to see anything coming out because it's way outside the cutoff frequency of the filter. And in fact, if I go and measure here, you can see that the signal is indeed at 5 megahertz. But let's turn the frequency from a sinusoid to a square wave. There we go. Now this square wave looks really ugly. This is not the square wave coming from the synthesizer. Remember, this square wave is going into the input impedance of the filter. So again, this is another thing for you to figure out and why this behavior happens. But check it out. I have a 5 megahertz square wave, but now I have an output from the filter. What is the output from the filter? What you should know readily already. Well, we can go ahead and measure it, and it is indeed at 15 megahertz. The third harmonic of the square wave is the only one that's going to go through the filter. So this filter, when fed with a 5 megahertz square wave, produces a 15 megahertz sine wave. So this is one way, not the best way, but this is one way of actually making frequency multipliers by having a lot of harmonics like a comb generator and then selecting the one that you're looking for. So you can see that it perfectly predicts the behavior of our filter and its characteristics and so on. So very interesting, cool little measurement to do. I just wanted to give you a brief look at it so you can see what can be done with this function. So it's because it is again correlated and everything is on the same screen, going through the different frequencies from the function generator is a good way to characterize different filters. If you have op amps and so on, you want to figure out what the bandpass response is or what the 3 dB cutoff frequency is. Very easy to do this way. Now there's a couple of other things that I want to show, but this is getting very long, so now you should have a fairly good idea of what can be done on this. Now I'm going to make a couple of more suggestions and a couple of other shortcomings. Now the aliasing definitely has to be fixed, but there is another feature which I think if it's added, it's going to add a huge value. So for the digital IOs, currently from the software, from the VirtualBench software, you can only set them to a 0 and 1 directly. But if you could program SPI, I2C, or other digital type interfaces in here the same way you can monitor them from the logic analyzer, that would be amazing. So you can define a bus, an I2C bus or an SPI bus, and then you can say that I want to have that bus be using, for example, well, you cannot, obviously you don't see it here because it's just an analyzer, but let's say there was an option here where you could say I want to use the digital IO0 as an SDA and I want to actually transmit these characters, and it will automatically translate that for you. That way you have now a complete system where you can use the digital IO to transmit your SPI commands and look at the logic analyzer to capture them and have a really nice and setup to be able to characterize or debug or hack a little module that you have without having to go through anything else, all really built into one software platform. Now all of this is obviously possible from the scripting capability of the instrument through LabVIEW and so on. You can do all of this without any problem, but this review was focused on just the software itself, not the automation capability of this instrument. And as I was just mentioning, you can do complete automation with the NI VirtualBench. You can have examples which are written in LabVIEW. You can write your own scripts. You can control every single instrument that's in here and do much more than what is available currently in this version of the software that we were looking at. So for automation is brilliant. Again, NI is the master of automation. That's what they do, and they've transferred some of that knowledge into this instrument, allowing you to make your own automation system. So if you're going to take advantage of that, it's definitely a really good idea. Now the question is, should you buy one? Well, as always, I can't tell you that. It depends on your needs, depends on your situation, but I have made some observations. As I was saying, if you're going to do automation for $2,000, which is the cost of this with everything that you saw, that's not a lot of money for full automation, especially for the other type of stuff that NI sells. So it is a pretty good deal. If you heavily take advantage of that aspect of it, I would recommend it right away. In an education system, it also makes really good sense because it's compact. You can tie it to a bench. You can have everybody use exactly the same instrument. It's backed up by NI. There are examples, and if there's going to be LabVIEW involved, then even better, because then you can program it directly with LabVIEW. It is perfect for that. I mean, just one other thing that I didn't have a chance to show you. I mean, check it out. It has an iPad app that is a replica of what is on the desktop, and it's written really well for touch. I was using it, it was working really nicely, and you can see, for example, I can turn the power supply on and off, and there you go, on and off, just like that. And it works really nice, and it's smooth, and it's through Wi-Fi. And imagine in an environment, in a class environment, you have this set up in the front, connected to something, and you just pass this from student to student, and they can, you know, examine the measurement, change the parameters of the measurement, and learn something right on the spot without having to even leave the desk. This is a brilliant idea, and I think it works so well. And it's just so cool to have the iPad in your hand and have all the displays on it. Now, if you're a beginner, it's also a pretty nice option. It's a little bit expensive, but it is something that has everything in it. If you don't have enough space on your desk, it could be something for you to consider. When there are some other products on the market, for example, like the Rigol 4-channel oscilloscope that costs $400, that has so many features in it. And that's a disruptive product, and it's hard to compete with that, of course. And if you already have some equipment at home, then it becomes harder to justify to buy something like this that replicates some of those. This is a type of instrument that does everything reasonably well, but doesn't excel at any specific instrument. So it is a good all-around unit, and if you don't have anything, then it might be a good start. But if you already have something, it may not be such an easy decision to make anymore. But that, again, at the end is up to you. Either way, I hope that you enjoyed the review, and that you learned something, and then you liked the experiments that I did. And feel free to leave a comment, rate the video, and let me know how you felt about it. And also feel free to answer the questions that I raised. If you happen to buy one of these, or if you're school considering one of these, or a batch of these, and you happen to buy it, let I know that you watched my video. I don't get any of the cut of the profits or sales or anything. It's just that I can have a good relationship with NI and continue to bring you this type of videos in the future. So I hope to see you next time, and talk to you in the comment section.